The lesson today is about quadratic equations. We are going into nonlinear relationships now. Now, in this lesson, you will understand that a quadratic equation is a nonlinear relationship, and the shape of a quadratic equation when plotted on the Cartesian plane is a parabola, and know how to solve quadratic equations using the Null factor law. Now, we know and we have learned what linear equations are. You can see that they've got a straight line, whether it's positive slope or negative slope. However, a nonlinear relationship, it is no longer a straight line. It could be curved up, curved down, or it could be any other funny shapes. Right, let's have a look at a little bit more. Here, again, these are all linear functions or linear relationships. In this case, these are non-linear functions or non-linear relationship. All right, a linear versus quadratic relationship. What are they? Linear, y equals mx plus c. You know there is a straight line, you know there's a gradient, and you know there's a constant. For a quadratic, it's y equals to ax squared plus bx plus c. This time, you must notice that there is an extra term with x squared, and note that for a quadratic function, a does not equal to 0. If it is 0, it becomes y equals bx plus c, which is linear. Now, just looking at this graph, only you know that for y equals ax squared plus bx, it has a y-intercept and it has two x-intercepts. Later, you will learn that not all quadratic relationship has x-intercept. At this stage, let's look at how do we solve for x. Now, this is a video of application of quadratic equations or parabola. Have a look. You can see that all these shapes are actually parabola. Roman aqueduct, roller coaster, even a fountain. This sort of application is widely used in terms of predicting, say, projectile, and looking at analyzing kicking a football or throwing a ball. Of course, it's used in games, Angry Birds. Can be written as y equals to ax squared plus bx plus c, like I mentioned just now, and a does not equal to 0. And we can actually solve for ax squared plus bx plus c when y equals to 0. Now let's have a look at the graphical significance of this. If we plot y equals to ax squared plus bx plus c on a Cartesian plane, we notice that there are, in this case, two x-intercepts. So at x-axis intercept, y equals to 0, and therefore when we solve ax squared plus c plus 0, plus c equals to 0 is actually solving for the y at the x-intercept. Now, let's have a look at the null factor law. So if there are products of two variables m(n) equals to 0, then m equals to 0, or n equals to 0, or m equals to n equals to 0. So to solve a quadratic equation, you need to move all terms to the left-hand side of the equation, factorize, and then use the null factor law to solve the equation. Now, if you have a variable or polynomial which is common factor, do not divide by it, factorize it instead. What I would suggest at this stage is that we are looking at a quadratic equation which crosses the x-axis either once or twice. We will look at quadratic equation which does not cross the x-axis a little bit later. Now let's solve this problem. So A, I need to factorize it. I need to take out the x as highest common factor. Therefore, it's x minus 6 equals to 0. So with the null factor law, we know that x equals to 0 or x minus 6 equals to 0. Therefore, in this case, x equals to 0 or plus 6. Now, if you actually divide it by x squared minus 6x equals to 0, let's do an equivalent equation of dividing by x throughout. We have x minus 6 equals to 0 and x therefore equals to 6. You know that this is not correct because you are missing x equals to 0. So remember, never ever do this. Do not divide by pronumerals. What about this one, part B? You can actually factorize it. Factorizing the left-hand side using factorizing monic, you know that this would be minus 2 minus 3 x. Therefore, x minus 2 equals to 0 or x minus 3 equals to 0. Therefore, x equals to 2 or 3. All right? Now, what about this one, x squared minus 16 equals to 0? This is actually difference of two squares or difference of two perfect square. So here, I know that I can factorize this as x minus 4 and x plus 4 equals to 0. Therefore, x equals to plus or minus 4. Alternatively, you can actually do it this way, x squared equals to 16. I add a 16 on the left-hand side, and therefore I add a 16 on the right-hand side. And now x equals to plus or minus square root of 16, which is plus or minus of 4. So either way is fine. What about the next one? X squared plus 25 equals to 0. Obviously, we can't actually factorize it. What about x squared equals to minus 25? And we now have x equals to plus or minus square root of minus 25. Here, you cannot solve this problem because minus square root of 25 does not exist in the real number. It is a complex number. You will learn complex number a little bit later. And you will notice that eventually when you start plotting something like x squared plus 25, it does not cross the x-axis. Alright, so I will just write it down. This quadratic equation, or y equals x squared plus 25, does not cross x-axis. Alright, how about doing something like this, solving x squared equals to 17x? We could actually, or we should move everything to the left-hand side. Minus 17x equals to 0. Therefore, factorizing it, x into x minus 17 equals to 0, x equals to 0 or 17. Same with this one. x squared minus 7x plus 6 equals to 0. Therefore, we know x equals to 0. Now, what would that be? 1 and 6. Minus 6 minus 1, therefore x equals to 1 or 6.